Right now, as you settle into the comfort of your evening, deep in the rainforests of Thailand, Brazil, and Africa, one of nature's most disturbing dramas is unfolding. An anak, perfectly healthy moments ago, suddenly stops what it's doing. Its movements become jerky, unnatural. It abandons its colony, its purpose, everything that defined its existence. It begins climbing. The ant isn't choosing to climb. Something else is driving it upward, overriding millions of years of evolved behavior. Inside its body, threading through its muscles and flooding its brain, a fungus is taking control, not killing Nok, not yet, but piloting. The fungus is driving the ant like a vehicle, and it knows exactly where it wants to go. This is Ophiocordyceps, unilateralis, the zombie ant fungus. It doesn't just kill its host, it controls it, manipulates it, uses it. The fungus turns a living creature into a puppet, making it perform actions that benefit the fungus while destroying the ant. It's mind control in nature, evolution's own horror story playing out on a microscopic stage. Perhaps you've heard of it, Fungus, the fungus that inspired video games and nightmares. Or perhaps this is your first encounter with one of evolution's most sinister innovations. Tonight, we're going to explore not just what happens when a fungus controls an ant's mind, but what this tells us about consciousness, free will, and the disturbing flexibility of behavior. So, let your mind wander into the humid understory of the rainforest, where ants march in orderly lines until one breaks rank, compelled by an intelligence not its own. To understand the zombie ant fungus, we must first understand its theater of operations, the tropical rainforest. These forests are nature's most competitive arenas. Every square centimeter is contested. Every resource is fought over. Every possible niche is filled. The rainforest isn't just trees and animals. It's a three-dimensional battlefield extending from the forest floor to the canopy 50 meters above. Each level has its own climate, its own ecosystem, its own rules. Temperature, humidity, and light change dramatically with height. What thrives on the ground would perish in the canopy, and vice versa. In this vertical world, carpenter ants, Camponotus, Castaneus, and related species are major players. They build their colonies high in the canopy, safe from flooding and many ground-based predators. Every day, worker ants travel up and down the trees, following chemical trails, foraging for food, maintaining their aerial empire. The forest floor, 20 to 30 meters below, is a different world. It's darker, more humid, cooler. The air is still and heavy with moisture. Fungal spores hang in the air, like invisible snow. It's perfect for fungi, but terrible for canopy-dwelling ants. They avoid it when they can, but sometimes, they can't avoid it. Sometimes, something makes them go there. Carpenter ants aren't solitary creatures. They're part of superorganisms, colonies of thousands of individuals acting as one. Each ant is like a cell in a larger body, with specialized roles and behaviors that benefit the whole. Worker ants follow strict behavioral programs, stay on marked trails, return to the colony regularly, avoid dangerous areas, respond to chemical signals, defend the colony, care for larvae. These behaviors are hardwired, refined over millions of years. An ant doesn't choose to follow trails, any more than your heart chooses to beat. It's automatic, instinctual, invariable, or so it should be. The colony depends on this predictability. If ants started behaving randomly, the colony would collapse. Social insects succeed because individuals sacrifice their autonomy for the collective good. They're biological robots running sophisticated but inflexible programs. This rigidity is both their strength and their vulnerability, because when something learns to hack the program, to insert its own code, the ant has no defense. It can't think its way out. It can't override its instincts with reason. It becomes a machine running malicious software. Ophiocordyceps unilateralis isn't just any fungus. It's a member of the cordyceps family, a group that has evolved one of nature's most sophisticated manipulation strategies. While most parasites simply feed on their hosts, Ophiocordyceps controls them. The fungus has been locked in an evolutionary arms race, with ants for perhaps 48 million years. Fossil evidence shows zombie ants in ancient leaf fossils, their death grip preserved in stone. For longer than primates have existed, this fungus has been perfecting its dark art. Each species of Ophiocordyceps specializes in one ant species. The fungus that zombifies carpenter ants can't affect other ants. This specificity suggests an incredibly intimate knowledge of the host's biology. The fungus doesn't just invade the ants, it knows the ant, understands it at a molecular level. The fungus exists as microscopic spores, each one a potential hijacker waiting for the right vehicle. The spores rain down from infected ant cadavers, positioned strategically above foraging trails. They're so small that thousands could fit on a pinhead, invisible and patient. The infection begins with a single spore landing on an ant's exoskeleton. This might seem like a harmless event. Though ants are covered in debris all the time. But this spore is different. Within hours it begins to act. The spore doesn't just sit on the surface, using specialized enzymes and mechanical pressure. It begins to drill through the ant's armor. The exoskeleton that protects ants from predators and environmental hazards becomes a prison, trapping them with their invader. The drilling process takes about 12 hours. The fungus secretes chitinases and proteases, enzymes that dissolve the ant's shell. Meanwhile, specialized structures called opressoria build up tremendous pressure, up to 8,000 kilopascals, enough to puncture synthetic plastics. Once through, the fungus enters the ant's hemal, insect equivalent of blood, but it doesn't immediately spread everywhere. It shows remarkable restraint, growing slowly, carefully, strategically. For the first 7 days after infection, the ant appears completely normal. It follows trails, forages for food, interacts with nestmates. The colony's social immunity, grooming each other, removing debris and potential pathogens, fails to detect anything wrong. Inside, the fungus is growing, but not as you might expect. Instead of forming a typical fungal network of branching filaments, mycelia, Ophiocordyceps, does something unprecedented. It breaks apart into single-celled yeast-like particles that float freely in the ant's hemolymph. These cells, called blastospores, multiply slowly. They consume nutrients from the ant's blood, but carefully avoid vital organs. The ant's brain, surprisingly, remains untouched. The fungus needs the brain functional. It's the control center it plans to hack. Dr. David Hughes, who has studied zombie ants for decades, describes this phase. The fungus is like a puppet master preparing strings. It's positioning itself throughout the ant's body, getting ready for the moment of control, but not yet pulling any strings. Around day 7-10, something remarkable happens. The individual fungal cells throughout the ant's body begin reconnecting. They form an intricate network that infiltrates 40 to 50% of the ant's body cavity. But this isn't random growth. It's precisely organized. The fungal network wraps around muscle fibers, but doesn't invade them. It surrounds nerve bundles, but doesn't penetrate. It's like a second nervous system, paralleling the ant's own. Modern scanning electron microscopy reveals fungal cells forming complex 3D structures around the ant's muscles, particularly in the legs and mandibles, jaws. Most remarkably, the fungus still avoids the brain, despite taking over half the ant's body mass. Despite having complete access, the fungus leaves the brain intact. This isn't mercy, it's strategy. The fungus doesn't need to be in the brain to control it. It just needs to control the inputs and outputs. Around noon, on the final day, something changes. The infected ant stops following trails. It stops responding to chemical signals from nestmates. It stops being an ant, behaviorally speaking. The transformation is abrupt. One moment, the ant is a functioning member of its society. The next, it's an individual with a singular, bizarre purpose. It begins walking erratically, stumbling, falling from branches. Other ants may try to help, but the infected ant ignores them. Then it begins to climb down. For a canopy-dwelling ant, this is wrong. Everything in its evolution says stay high, stay safe. The forest floor is danger, predators, flooding, competing colonies, but the ant ascends anyway, driven by an urge it cannot resist. The fungus is releasing chemicals. We don't know exactly which ones that manipulate the ant's behavior. These might be mimicking the ant's own neurotransmitters, or they might be entirely novel compounds. The result is the same. The ant's behavioral program is overwritten. The infected ant's journey to the forest floor is painful to watch. It moves and stutters and staggers, like a malfunctioning robot. Sometimes it falls, catches itself, continues. Sometimes it walks in circles before resuming its descent. This isn't random wandering. The ant is searching for something specific, though it doesn't know what. The fungus is driving it toward precise conditions, 20 to 30 centimeters above the forest floor, 94 to 95% humidity, temperature around 25 degrees Celsius, north-northwest orientation to avoid direct sun. The fungus needs these conditions to complete its life cycle. Too high, and it's too dry for spore development. Too low, and the spores won't disperse properly. Wrong orientation and temperature fluctuations will kill the developing fungus. How does the fungus know when it's found the right spot? We don't fully understand. It might sense humidity through the ant's spiracles breathing holes. It might detect temperature through chemical reactions. It might even use the ant's own sensory systems, interpreting the signals for its own purposes. The most extraordinary part happens at solar noon once when the sun is highest in the sky. Across the forest, all ants infected by the same fungus species perform their death bite at almost exactly the same time. The ant finds a leaf vein wounds, specifically a major vein on the underside of a leaf. It opens its mandibles wide, then bites down with tremendous force. But this isn't a normal bite. The fungus has been atrophying the muscles that open the mandibles while strengthening the muscles that close them. The bite is so powerful it often damages the ant's head capsule. The mandibles lock in place, a death grip that will persist long after the ant dies. Even after decomposition, the head and mandibles often remain attached to the leaf. Immediately after biting, the fungus destroys the ant's mandible muscles. The ant couldn't let go, even if it wanted to. It's permanently anchored to its final perch. Once the ant is secured, the fungus no longer needs to maintain the pretense. Within hours it begins consuming the ant from the inside out. The brain, previously untouched, is among the first organs devoured. The ant dies hanging from its leaf, typically within 24 moons 48 hours of the death bite. But death doesn't end the horror. It's just the beginning of the fungus's reproductive phase. Recent genomic studies have revealed the sophisticated chemistry behind zombie ant control. Enterotoxins. The fungus produces compounds similar to bacterial toxins that affect nerve signal transmission. Ergot alkaloids. Similar to compounds in the ergot fungus, famous for causing hallucinations, these might alter the ant's perception and behavior. Polypeptides. These diverse compounds could mimic ant pheromones or neurotransmitters. Novel proteins. Ophiocordyceps produces unique proteins found nowhere else in nature, suggesting evolution of specific ant manipulation tools. The fungus's genome shows evidence of horizontal gene transfer. It has stolen genes from bacteria and other organisms, assembling a toolkit specifically for ant control. The zombie ant phenomenon is a perfect example of what Richard Dawkins called the extended phenotype, when one organism's genes control another organism's behavior. The fungus's genes are expressed not just in fungal cells but in ant behavior. To foresee the ant's death march, the synchronized timing, the specific bite location, these are fungal behaviors expressed through an ant body. The ant becomes part of the fungus's phenotype. This raises profound questions. Where does the ant end and the fungus begin? Who or what is making the decisions? Is the infected ant still an ant, or has it become something else entirely? Ant colonies aren't defenseless against the zombie fungus. They've evolved sophisticated countermeasures. Behavioral fever. Some ants deliberately seek high temperatures when infected, attempting to kill the fungus with heat. Social immunity. Ants groom each other constantly, removing spores before infection. Graveyard effect. Colonies establish graveyards far from the nest where they dump infected individuals. Adaptive avoidance. Some colonies learn to avoid areas where infections have occurred. Most remarkably, some ants seem to recognize infected nestmates before symptoms appear. They forcibly remove them from the colony, carrying them far away. How they detect early infection remains unknown. The zombie ant system is locked in constant evolution. The fungus evolves better control mechanisms. The ants evolve better resistance. The fungus evolves ways around the resistance. The cycle continues. Some ant species have developed remarkable immunity. They live in the same forests, encounter the same spores, but never get infected. Their secret might lie in different exoskeleton chemistry, antimicrobial secretions, behavioral adaptations, symbiotic bacteria that fight the fungus. Meanwhile, the fungus diversifies. There are over 140 species of Ophiocordyceps, each specialized for different hosts. Some create zombie beetles, zombie flies, zombie spiders. Each relationship is unique, fine-tuned over millions of years. The zombie ant phenomenon triggers deep psychological horror in humans. It violates our most fundamental assumption, that our minds are our own. The idea of something else controlling our bodies, making us do things against our will, is the stuff of nightmares. Horror fiction has long explored this fear. Possession, mind control, puppet masters, but Ophiocordyceps is real. It exists. Right now, thousands of ants are being marched to their deaths by an intelligence not their own. The fungus doesn't just kill mites, it uses. The ant becomes a vehicle, a tool, a means to an end. Its individuality is erased, its purpose rewritten. It dies not for its colony, not for its genes, but for something utterly alien to its existence. Dr. David Hughes describes watching infected ants. There's something deeply unsettling about seeing an ant behave so wrongly. You know it's just an ant, but watching it struggle against its own body, seeing it forced to act against its nature, it affects you. Yet, for all its horror, the zombie ant fungus is also a marvel of evolution. The precision of control, the complexity of manipulation, the perfect timings, it's a masterpiece of biological engineering. Consider what the fungus achieves. Chemical precision exceeding our best pharmaceuticals. Behavioral control. We can't replicate with technology. Navigation without sensory organs, timing without a clock, consistency across thousands of infections. The fungus solves problems that challenge our most advanced science. How do you control a brain without entering it? How do you navigate using another organism's senses? How do you time events without experiencing time? The zombie ant forces us to confront uncomfortable questions about consciousness and free will. Does the ant suffer? We assume it does, but can we know? Does the ant experience its loss of control, or does consciousness require the very autonomy the fungus destroys? Where is the ant's self? If behavior defines identity, does the ant cease to exist once infected? Is the zombie ant still an ant, or has it become part of the fungus? What is free will? The healthy ant follows genetic programming. The infected ant follows fungal programming. Is there a meaningful difference? Could this happen to us? Not with Ophiocordyceps, which is specialized for insects, but other parasites affect mammalian behavior. Where's the line between influence and control? Humans aren't immune to parasitic behavioral manipulation. Toxoplasma gondii, a protozoan parasite, infects about 1/3 of humanity. While not as dramatic as Ophiocordyceps, it appears to alter human behavior. increased risk-taking slower, reaction times personality, changes possible links to schizophrenia, altered testosterone levels in men, changes in attraction patterns, toxoplasma needs to get from rodents, intermediate hosts to cats, definitive hosts. It makes infected rodents less fearful of cat odor, even attracted to it. The rodents get eaten. The parasite reaches cats. The cycle continues. In humans, accidental hosts, toxoplasma still causes behavioral changes. We're not being driven to cats to be eaten, but the parasite's chemical manipulation affects us anyway. It's a reminder that we're not as in control as we think. Rabies virus is another behavioral manipulator. It makes infected animals aggressive, more likely to bite. The virus concentrates in saliva and spreads through bites. The aggression isn't random minus. It's the virus's dispersal strategy. In humans, rabies causes hydrophobia, fear of water, which prevents dilution of virus-rich saliva. It causes aggression, confusion, and hypersexuality. The virus hijacks behavior to spread itself, just like Ophiocordyceps. Even our normal gut bacteria influence behavior. Certain bacteria produce neurotransmitters. Gut microbiome affects anxiety and depression. Bacteria can trigger cravings for foods they prefer. Microbial diversity correlates with personality traits. We're not individuals but ecosystems. Millions of organisms live in and on us, potentially influencing our thoughts, feelings, and behaviors. The line between self and other is blurrier than we imagine. The zombie ant fungus has captured public imagination. Video games, The Last of Us, features a mutated cordyceps that infects humans, creating zombie-like creatures. The game explores themes of autonomy, survival, and what makes us human. Television, the HBO adaptation brought zombie fungus to mainstream awareness, triggering discussions about pandemic preparedness and biological warfare. Literature, numerous books feature cordyceps-inspired parasites, exploring body horror and loss of control. Documentary films, nature documentaries, particularly BBC's Planet Earth, brought stunning footage of zombie ants to global audiences. Ophiocordyceps has inspired research across disciplines, neuroscience, understanding how the fungus controls behavior without entering the brain could reveal new principles of neural control. Pharmacology, the fungus's chemical toolkit might yield new drugs for neurological conditions. Robotics, the efficient control mechanism, inspires new approaches to biorobotics. Agriculture, understanding fungal manipulation could lead to novel pest control methods. The zombie ant has become a touchstone for philosophical debates. Consciousness, what is the minimum requirement for consciousness? Does the ant have subjective experience, free will? If all behavior is ultimately chemical, do we have more free will than the zombie ant? Identity, what defines an individual? Mud, the body, the brain, or the behavior? Ethics, if we could cure infected ants, should we? Are we obligated to prevent suffering in insects? New technologies are revealing previously hidden aspects. 3D, electron microscopy, shows the precise structure of fungal networks inside ants. Metabolomics, identifies the exact chemicals the fungus produces. Transcriptomics, reveals which genes are active during infection. Time-lapse photography, captures the full infection cycle in unprecedented detail. CT scanning, allows non-destructive study of infected ants. In the last 5 years, researchers have discovered the fungus forms distinct structures around different muscles. Infection triggers specific immune responses that fail. Some ants have genetic resistance to infection. The death bite involves multiple synchronized mechanisms. Environmental factors affect infection success rates. Major mysteries remain. How does the fungus navigate? We don't know how it finds the perfect death spot. What triggers the death bite timing? The synchronization mechanism is unknown. Why spare the brain? The evolutionary advantage of avoiding the brain isn't clear. How did this evolve? The step-by-step evolution of such complex manipulation is mysterious. Can it be stopped? No cure exists for infected ants. Ophiocordyceps species are found in tropical forests worldwide. South America. The Amazon basin has the highest diversity, with dozens of species. Africa. Central African rainforests harbor unique species. Asia, Thailand, and Malaysia are hotspots for zombie ant diversity. Australia. Northern rainforests have endemic species. Each location has its own species pairs specific fungi for specific ants. The relationship is so specialized that introducing a fungus to a new location rarely results in successful infection of local ants. Global warming is affecting zombie ant dynamics. Range expansion. Some species are spreading to previously temperate areas. Altitude shifts. Infections are occurring at higher elevations. Timing changes. The seasonal patterns of infection are shifting. Host switches. Stress might make new ant species vulnerable. Climate change could unleash zombie ant fungi on previously safe ant populations, potentially disrupting entire ecosystems. The zombie ant system faces threats. Habitat loss. Deforestation destroys the complex ecosystems both organisms need. Pesticides. Agricultural chemicals affect both ants and fungi. Invasive species. Non-native ants might lack resistance to local fungi. Collection pressure. Scientific and commercial collection impacts populations. Some Ophiocordyceps species might go extinct before we understand them, taking their secrets with them. Ophiocordyceps produces powerful antimicrobials, antibacterial agents that prevent secondary infection, antifungal compounds that eliminate competition, antiviral molecules of unknown function. These compounds work in the challenging environment of an insect body. They might yield new medicines for resistant infections. The fungus must suppress the ant's immune system without killing it immediately. This delicate balance could inspire new immunosuppressive drugs for organ transplants or autoimmune diseases. The behavior-controlling chemicals might lead to new treatments for neurological disorders, better understanding of neurotransmitter systems, novel approaches to behavioral therapy, insights into addiction and compulsion. Some cordyceps species show anti-cancer properties. The precise cell-targeting mechanisms of Ophiocordyceps could inspire targeted cancer therapies. Even after the ant dies, the fungus maintains control. The death grip persists through decomposition. The ant's head remains attached to the leaf for weeks or months, held by locked mandibles. This post-mortem control is perhaps the most disturbing aspect. Death doesn't free the ant. It remains a tool, a platform, a possession of the fungus even in death. About 2-3 weeks after the ant's death, something emerges from its head. A stalk grows from the back of the ant's head, reaching several centimeters into the air. This is the fungus's fruiting body, its reproductive structure. The stalk is positioned precisely. Too short, and spores won't disperse. Too long, and it might break. The fungus has calculated the optimal height for its location. At the stalk's tip, a bulbous structure develops, the spore capsule. Inside, millions of spores develop, each one capable of creating another zombie ant. When conditions are right, usually during humid nights, the capsule ruptures. Spores rain down onto the forest floor below, covering the ant trails where healthy ants travel. The positioning is perfect. The infected ant bit into a leaf above a trail. The fruiting body extends from the ant's head, positioning the spore release directly over passing ants. Even in death, the ant serves the fungus's purpose. Each spore is a potential hijacker. The cycle begins again. The evolution of zombie ant behavior is almost incomprehensible. How does random mutation and selection produce such precise control? The fungus must recognize the correct host. Species penetrate its defenses, grow without killing immediately, produce behavior-altering chemicals, navigate using the host's senses, time events precisely, position the host perfectly, maintain control after death. Each step seems impossibly complex. Together, they represent one of evolution's most sophisticated achievements. In the last 5 years, researchers have discovered the fungus forms distinct structures around different muscles. Infection triggers specific immune responses that fail. Some ants have genetic resistance to infection. The death bite involves multiple synchronized mechanisms. Environmental factors affect infection success rates. Major mysteries remain. How does the fungus navigate? We don't know how it finds the perfect death spot. What triggers the death bite timing? The synchronization mechanism is unknown. Why spare the brain? The evolutionary advantage of avoiding the brain isn't clear. How did this evolve? The step-by-step evolution of such complex manipulation is mysterious. Can it be stopped? No cure exists for infected ants. Ophiocordyceps species are found in tropical forests worldwide. South America. The Amazon basin has the highest diversity, with dozens of species. Africa. Central African rainforests harbor unique species. Asia, Thailand, and Malaysia are hotspots for zombie ant diversity. Australia. Northern rainforests have endemic species. Each location has its own species pairs specific fungi for specific ants. The relationship is so specialized that introducing a fungus to a new location rarely results in successful infection of local ants. Global warming is affecting zombie ant dynamics. Range expansion. Some species are spreading to previously temperate areas. Altitude shifts. Infections are occurring at higher elevations. Timing changes. The seasonal patterns of infection are shifting. Host switches. Stress might make new ant species vulnerable. Climate change could unleash zombie ant fungi on previously safe ant populations, potentially disrupting entire ecosystems. The zombie ant system faces threats. Habitat loss. Deforestation destroys the complex ecosystems both organisms need. Pesticides. Agricultural chemicals affect both ants and fungi. Invasive species. Non-native ants might lack resistance to local fungi. Collection pressure. Scientific and commercial collection impacts populations. Some Ophiocordyceps species might go extinct before we understand them, taking their secrets with them. Ophiocordyceps produces powerful antimicrobials, antibacterial agents that prevent secondary infection, antifungal compounds that eliminate competition, antiviral molecules of unknown function. These compounds work in the challenging environment of an insect body. They might yield new medicines for resistant infections. The fungus must suppress the ant's immune system without killing it immediately. This delicate balance could inspire new immunosuppressive drugs for organ transplants or autoimmune diseases. The behavior-controlling chemicals might lead to new treatments for neurological disorders, better understanding of neurotransmitter systems, novel approaches to behavioral therapy, insights into addiction and compulsion. Some cordyceps species show anti-cancer properties. The precise cell-targeting mechanisms of Ophiocordyceps could inspire targeted cancer therapies. Even after the ant dies, the fungus maintains control. The death grip persists through decomposition. The ant's head remains attached to the leaf for weeks or months, held by locked mandibles. This post-mortem control is perhaps the most disturbing aspect. Death doesn't free the ant. It remains a tool, a platform, a possession of the fungus even in death. About 2-3 weeks after the ant's death, something emerges from its head. A stalk grows from the back of the ant's head, reaching several centimeters into the air. This is the fungus's fruiting body, its reproductive structure. The stalk is positioned precisely. Too short, and spores won't disperse. Too long, and it might break. The fungus has calculated the optimal height for its location. At the stalk's tip, a bulbous structure develops, the spore capsule. Inside, millions of spores develop, each one capable of creating another zombie ant. When conditions are right, usually during humid nights, the capsule ruptures. Spores rain down onto the forest floor below, covering the ant trails where healthy ants travel. The positioning is perfect. The infected ant bit into a leaf above a trail. The fruiting body, extends from the ant's head, positioning the spore release directly over passing ants. Even in death, the ant serves the fungus's purpose. Each spore is a potential hijacker. The cycle begins again. The evolution of zombie ant behavior is almost incomprehensible. How does random mutation and selection produce such precise control? The fungus must recognize the correct host. Species penetrate its defenses, grow without killing immediately, produce behavior-altering chemicals, navigate using the host's senses, time events precisely, position the host perfectly, maintain control after death. Each step seems impossibly complex. Together, they represent one of evolution's most sophisticated achievements. The more I learned, the more disturbing it became. This wasn't crude parasitism. It was precise, sophisticated, purposeful. The fungus knew things: how to navigate, when to act, where to position the ant. It showed intention without consciousness, purpose without awareness. It made me question the nature of intelligence, consciousness, and will. If a fungus can show such sophisticated behavior without a brain, what does that mean for consciousness? If chemicals can control behavior so precisely, what does that mean for free will? There's an awful beauty to the zombie ant system. The precision, the complexity, the perfect ecological integration. It's evolution at its most creative and cruel. The fungus and ant have been locked in this dance for millions of years, each trying to outwit the other, each pushing the other to evolve. It's produced one of nature's most sophisticated interactions. Is it horrible? Yes. Is it fascinating? Absolutely. Is it natural? Completely. Right now, as you prepare for sleep, the drama continues in rainforests worldwide. Spores are falling like invisible snow. Ants are following trails, unaware of the danger. Some already carry the fungus within them, their fate sealed but not yet manifest. As darkness falls in the rainforest, infected ants are beginning their final climb. They move against their will, driven by imperatives they don't understand. They're searching for the perfect leaf, the perfect position, the perfect place to die. At this moment, thousands of ants are biting into leaves with their dying strength. They're anchoring themselves for a death that serves another. Their individual stories are ending, but the fungus's story continues. Tomorrow, in rainforests around the world, colony workers will find their missing sisters. They'll find them hanging from leaves, jaws locked in death. Some colonies will recognize the danger and remove the bodies. Others will abandon the area. But it's too late. The fungus is already growing, already preparing its fruiting body. In a few weeks, spores will rain down again. The cycle continues. This has been happening for millions of years. It will continue for millions more. Long after humans are gone, ants will still be climbing to their fungus-directed deaths. As you drift towards sleep, consider the parallels. Sleep is a kind of possession too. Consciousness recedes. Control is surrendered. Dreams drive behavior in that internal world. You become a passenger in your own mind. But unlike the zombie ant, you wake up. Autonomy returns. The self reasserts. You're lucky in that way. Your loss of control is temporary, natural, restorative. The zombie ant reminds us that control is precious, that autonomy is not guaranteed, that the self is more fragile than we imagine. The zombie ant fungus teaches us about control, Midas, how it can be taken, how it can be given, how it can be lost. We think we're in control of our lives, our decisions, our behaviors. The zombie ant thought the same. Every influence on our behavior, from hormones to social pressure to gut bacteria, is a tiny fungus, pulling us in directions we might not choose. We're all partially zombified, following imperatives from sources we don't fully understand, but awareness might be our salvation. Unlike the ant, we can recognize manipulation. We can question our impulses. We can ask, is this my desire or something else's? The zombie ant dies serving the fungus's purpose, but don't we all die serving something's purpose? Our genes, our societies, our ecosystems. Death always serves life, just not always our own. The horror isn't that the ant dies for another's benefit. It's that it has no choice. It can't decide. Its death has meaning. It can't choose its final purpose. We can. That might be what separates us from the zombie ant. Not immunity from control, but the ability to recognize and sometimes resist it. The fungus and ant are separate species that become one functional unit. The ant's behavior becomes the fungus's extended body. Two organisms merge into one horrifying whole. But isn't all life similarly connected? We're all part of food webs, ecosystems, the global organism of Earth. We affect each other, control each other, depend on each other. The zombie ant is just an extreme example of life's fundamental interconnection. The horror comes from seeing this connection made visible, made undeniable. We prefer to imagine ourselves as individuals. The zombie ant reminds us that individuality is always partial, always contingent, always vulnerable. The zombie ant fungus is simultaneously wonderful and horrible. It's evolution's genius and nature's cruelty. It's sophisticated beyond our technology and brutal beyond our ethics. This duality exists throughout nature, beauty and horror intertwined, creation and destruction inseparable, life feeding on life. The zombie ant just makes this visible in particularly stark terms. Perhaps the lesson is to accept both miters, to marvel at the fungus's sophistication while mourning the ant's fate, to appreciate the system while recognizing its cruelty, to see nature as it is, neither kind nor cruel, but endlessly creative in ways that sometimes horrify us. Despite decades of research, the zombie ant fungus remains largely mysterious. We don't know how it navigates. We don't know how it times events. We don't know how it evolved. We don't even know what the ant experiences. Hugh's mystery is humbling. It reminds us that nature exceeds our understanding, that evolution produces solutions we can't imagine, that life is more creative than our theories. The zombie ant tells us that the world is stranger than we know, possibly stranger than we can know, and that's either terrifying or wonderful, depending on your perspective. After all our exploration, what do we know for certain? A fungus can control an ant's behavior with precision exceeding our best technology. This control serves the fungus's reproduction at the cost of the ant's life. The system has existed for millions of years. It continues today. These facts are disturbing enough, without embellishment. The list of unknowns is longer. The ant's subjective experience, the exact control mechanisms, the evolutionary pathway, the full ecological implications, the potential for similar systems in other species. These unknowns leave room for both wonder and worry. Based on evidence and reasoning, we suspect the ant suffers, if insects can suffer. Similar systems exist undiscovered. Behavioral manipulation is common in nature. We ourselves are subject to various controls. The line between self and other is blurrier than we think. Suspicions challenge comfortable assumptions about autonomy and individuality. The zombie ant fungus invites us to question our assumed autonomy, recognize our interconnection with other life, appreciate the sophistication of evolution, confront the reality of nature's cruelty, wonder at life's endless creativity. This invitation is uncomfortable but valuable. Picture one last scene. A rainforest at dawn. Mist rises from the forest floor. An ant hangs from a leaf, dead, jaws locked in place. From its head, a single stalk reaches toward the canopy. At its tip, a capsule swells with spores. Below, a trail of healthy ants marches past, following their ancient routes. They don't look up. They don't know that death watches from above, waiting to rain down. One ant pauses, cleans its antenna, continues walking. Perhaps it brushed off a spore. Perhaps it's already doomed. Time will tell. The forest doesn't care. The sun rises higher. Life continues in all its terrible beauty. As you descend towards sleep, carry with you the image of the zombie ant. Not as nightmare but as reminder that control is precious and precarious, that individuality is real but limited, that nature is creative beyond imagination, that horror and wonder are not opposites but partners, that we are all connected in ways we barely understand. Let sleep take you gently, grateful that your loss of control is temporary, that your dreams are your own, that tomorrow you'll wake with autonomy restored. The zombie ants have no such luck. They march to deaths not their own, serving purposes they can't comprehend, becoming vehicles for alien imperatives. But even in that horror, there's a strange beauty. The beauty of life's endless creativity, its refusal to be simple, its insistence on finding ever more complex ways to continue. Sleep now, and dream your own dreams. Tomorrow you'll wake as yourself. The ants won't be so fortunate, but life, terrible and beautiful, will continue, as it always has, as it always will, until even the fungi are fossils, and something else dances on their graves. In sterile laboratories around the world, scientists attempt to recreate the zombie ant phenomenon under controlled conditions. These studies reveal details impossible to observe in the rainforest's chaos. At Penn State's Hughes lab, infected ants are kept in precisely controlled chambers. Temperature, humidity, and light cycles mimic the rainforest. High-speed cameras record every movement. The transformation from healthy ant to zombie unfolds in excruciating detail. The laboratory observations reveal subtleties missed in the field, pre-symptomatic changes, days before obvious symptoms. Infected ants show micro-behavioral changes. They pause more frequently. Their antenna movements become irregular. They spend more time grooming, as if trying to remove something they sense but can't identify. Social rejection. Nestmates begin avoiding infected ants 2–3 days before symptoms appear. They can somehow detect infection before any visible signs. This early detection might be chemical. Infected ants may emit different pheromones or behavioral subtle movement changes that healthy ants recognize. The wandering phase. Before the final death march, infected ants go through a wandering phase lasting 12–24 hours. They walk in elaborate patterns that seem random, but analysis reveals recurring motifs. They're not lost, they're searching, following parameters programmed by the fungus. Muscular atrophy. MRI scans of infected ants show selective muscle atrophy beginning days before the death bite. The fungus weakens muscles used for normal behaviors while strengthening those needed for the death grip. It's essentially redesigning the ant's muscular system for its own purposes. Mass spectrometry reveals the complex chemical conversation between fungus and ant. The fungus produces over 300 unique compounds during infection. These include neurotransmitter analogs, molecules that mimic dopamine, serotonin, and octopamine, the insect equivalent of norepinephrine. These don't just interfere with normal signaling miters. They create new signal patterns, enzyme inhibitors, compounds that block specific metabolic pathways, forcing the ant cells to rely on fungal metabolism. Immunosuppressants, a cocktail of proteins that specifically target the ant's immune cells, preventing them from recognizing the fungus as foreign. Clock proteins, molecules that interfere with the ant's circadian rhythms, possibly explaining the synchronized timing of the death bite. Novel alkaloids, completely unique compounds found nowhere else in nature, suggesting millions of years of specialized evolution. The fungus doesn't flood the ant with these chemicals all at once. It releases them in precise sequences, like a conductor bringing in different sections of an orchestra. The timing is crucial. Miters too early, and the ant's immune system might respond too late, and the ant might die before reaching the optimal position. Advanced imaging techniques reveal the fungus's physical structure inside the ant. Hyphal networks. The fungus forms elaborate three-dimensional networks that follow specific anatomical paths. These aren't random miters. They trace the ant's nervous system, wrapping around nerve bundles without penetrating them. Metabolic zones. Different regions of fungal growth show different metabolic activity. Some areas are dormant, others highly active. The pattern suggests functional specialization. Different parts of the fungal network serve different purposes. Interface cells, Where fungus meets ant tissue, specialized cells form. These interface cells have characteristics of both organisms. They're chimeric, part ant, part fungus. They might be how the fungus reads the ant's internal state. Preserved structures. Remarkably, the fungus preserves certain ant structures intact until the very end. The brain, major nerve pathways, and sensory organs remain functional. The fungus needs these systems working to achieve its goals. Not all laboratory infections succeed, and failures are informative. Temperature sensitivity. A few degrees too warm or cool, and the fungus can't establish control. The ant dies, but without the characteristic death march and bite. This suggests the behavioral manipulation requires precise biochemical conditions. Resistant individuals. About 5% of ants from susceptible species show natural resistance. They get infected, but don't develop symptoms. Genetic analysis of these individuals might reveal the molecular basis of resistance. Timing failures. Sometimes infected ants perform the death bite at the wrong time or place. These failures suggest the complexity of the fungus's navigation and timing systems. Incomplete takeover. In some cases, the fungus establishes partial but not complete control. Ants show some zombie behaviors, but retain some normal behaviors. These intermediate states reveal the gradual nature of the takeover. The zombie ant phenomenon is not one story but hundreds. Ophiocordyceps unilateralis sensulato. What was once thought to be one species is actually a complex of over 140 species, each specialized for different ant hosts. Geographic variance. The same ant species in different locations is infected by different fungal species. Brazilian carpenter ants face different fungi than Thai carpenter ants. Behavioral variations. Different fungus-ant combinations show different manipulation behaviors. Some create zombies that bite bark instead of leaves. Others make ants climb down instead of up. Each variation is precisely adapted to local conditions. Host switching events. Occasionally, a fungus jumps to a new host species. These events are usually unsuccessful, but rarely, they establish new zombie systems. We might be witnessing evolution in action. Zombie ant fungi play crucial ecological roles. Population control. They prevent any single ant species from dominating. When an ant colony grows too large, infection rates increase, limiting population growth. Nutrient cycling. Infected ants transport nutrients from the canopy to the forest floor. The fungus essentially creates an elevator service for organic matter. Biodiversity maintenance. By controlling dominant species, the fungi maintain space for other organisms. They're ecosystem engineers, shaping community structure through selective predation. Food web nodes. The fruiting bodies feed various invertebrates. Some species specialize in eating Ophiocordyceps mushrooms. The fungus that kills ants feeds other forest inhabitants. Global warming is reshaping zombie ant dynamics. Altitude migration. As temperatures rise, optimal infection conditions move upslope. Fungi and ants that never encountered each other are now meeting, creating new zombie systems. Seasonal shifts. The timing of infection cycles is changing. What were once seasonal patterns are becoming year-round in some locations. Range expansions. Some Ophiocordyceps species are spreading beyond their historical ranges, potentially encountering naive ant populations with no evolved defenses. Extinction risks. Other species are losing habitat as temperature and humidity patterns change. Some zombie ant systems that existed for millions of years might disappear in decades. Beyond toxoplasma, humans host various behavioral manipulators, gut bacteria, and mood. Specific bacterial strains produce neurotransmitters that affect mood and behavior. Lactobacillus produces GABA, affecting anxiety. Enterococcus produces serotonin, affecting happiness. We're not individuals but communities. Our moods partially determined by microbial demographics, parasitic worms and allergies. Some helminth infections reduce allergic responses and autoimmune conditions. The worms manipulate our immune system for their survival, but we might benefit too. Some people deliberately infect themselves with worms to treat autoimmune diseases, viruses, and sociability. Several viruses make hosts more social during early infection before symptoms appear. This increases transmission opportunities. We think we're choosing to socialize, but virus-induced chemical changes might be driving us. Fungal influences. Certain Candida species, when overgrown, produce chemicals that trigger sugar cravings. The fungus manipulates our behavior to obtain its preferred food source. Richard Dawkins coined meme to describe ideas that spread like parasites. Earworms. Songs that get stuck in your head are mental parasites, using your neural resources for their replication. Viral ideas. Some ideas spread not because they're true or useful, but because they trigger strong emotions or exploit cognitive biases. Behavioral contagions. Yawning, laughter, and emotions spread through groups like infections. We catch behaviors from others without conscious choice. Social media algorithms. Digital systems that manipulate behavior for engagement might be considered technological parasites, hijacking reward systems for profit. The zombie ant reminds us that behavioral control comes in many forms, not all biological. The infected ant poses a version of the ancient ship of Theseus paradox. As the fungus replaces the ant's behavioral programming, at what point does it cease to be the original ant? If the body remains but all behaviors change, is it the same organism? The fungus doesn't replace the ant's cells initially, it just controls them. But control without replacement might be more profound than physical replacement. The ant's matter remains, but its pattern, its essential antness, is overwritten. Philosophers argue that minds extend beyond brains to include tools and environment. The zombie ant represents an extreme case. The fungus becomes part of the ant's extended mind but a parasitic part. The ant's decision-making system now includes fungal networks. Its goals incorporate fungal imperatives. This raises questions. Where does the ant's mind end and the fungus's begin? Can two minds occupy one body? Is the infected ant a single organism with conflicting goals or two organisms sharing hardware? We assume other humans have conscious experiences like ours, but we can't prove it. The zombie ant amplifies this problem. Does the healthy ant have consciousness? If so, does it persist during infection? Does the fungus have consciousness? Is the infected ant conscious of its loss of control? We project suffering onto the infected ant, but this might be anthropomorphism. Perhaps there's no ant to suffer, just chemical reactions playing out. Or perhaps there's more consciousness than we imagine, both ant and fungus experiencing their fatal interaction. The zombie ant system inspires biotechnology, targeted drug delivery. The fungus delivers chemicals precisely where and when needed. Similar systems could deliver medicine to specific organs at specific times. Behavioral therapeutics. Understanding fungal behavioral control might lead to treatments for behavioral disorders. Not mind control, but gentle correction of problematic patterns. Immunomodulation. The fungus's immunosuppression is selective and temporary. Similar approaches might treat autoimmune diseases without leaving patients defenseless. Neural interfaces. The fungus controls behavior without entering the brain. This might inspire non-invasive neural control technologies. The zombie ant raises ethical concerns about research directions, dual-use potential. Behavioral control research could be weaponized. Understanding how to control behavior means understanding how to manipulate it. Enhancement versus treatment. If we can control behavior, should we? Where's the line between treating illness and enhancing performance? Consent issues. Could behavioral control technologies be used without consent? The zombie ant can't refuse infection. Identity questions. If we can change behavior fundamentally, do we change identity? Would treating depression by copying fungal techniques preserve or destroy the self? Ants have evolved sophisticated anti-zombie strategies. Chemical detection. Some ants produce detection pheromones that mark infected individuals. These death markers trigger immediate exile responses. Behavioral immunity. Colonies that experience infections develop behavioral traditions. avoiding certain areas, changing foraging patterns, increasing grooming frequency. Genetic resistance. Some populations have alleles that confer resistance. These might code for different surface proteins that prevent spore attachment. Enhanced immune responses. Behavioral changes that reduce exposure. Social sacrifice. Some infected ants seem to recognize their condition and voluntarily leave the colony, dying far from their sisters. This might be ant altruism or early fungal manipulation. The fungus evolves around ant defenses. Immunological cloaking. Some strains produce proteins that mimic ant proteins, avoiding immune detection. Behavioral masking. The fungus might suppress early symptoms longer, avoiding social detection until it's too late. Chemical warfare. New compounds that overcome ant resistance appear regularly. The fungus's chemical arsenal constantly expands. Timing shifts. Fungal strains that act faster might avoid some ant defenses, completing their cycle before colonies can respond. The zombie ant system exemplifies the Red Queen hypothesis. Organisms must constantly evolve just to maintain their position relative to co-evolving organisms. Neither ant nor fungus can afford to stop evolving. Any pause means the other gains advantage. They're running on an evolutionary treadmill, neither able to step off. This perpetual race has produced extraordinary sophistication on both sides. The complexity we observe today represents millions of years of move and countermove. Dr. Charissa de Becker, who studies zombie ants, describes a typical research day. 4 a.m. mens arrive at field site before dawn. Infected ants typically bite leaves between 9 a.m. and noon. Need to be ready. 5:30 a.m. mens located 3 infected ants in wandering phase. Mark their positions. Begin filming. 1 shows classic spiraling walk pattern. 8:45 a.m. mens. First ant begins ascending behavior. It's chosen a sapling about 3 meters from the main trail. Temperature 24 degrees Celsius. Humidity 92%. 9:20 a.m. mens. Ant reaches 23 centimeters height. Begins examining leaves. Rejects first 4. This selection process remains mysterious. 9:35 a.m. mens. Death bite initiated. Ant positions itself on major vein. Underside of leaf, northwest orientation. The precision is uncanny. 9:37 a.m. mens. Bite complete. Ant is now locked in place. Within hours it will be dead. I mark the location for long-term observation. 2 p.m. mens. Return to lab, with samples. Infected ants sectioned for microscopy. The fungal network is beautiful and horrifying. Perfect biological engineering. 8 p.m. mens. Data analysis. Today's observations add 3 more data points to our timing study. The synchronization is real, but the mechanism remains unknown. 11 p.m. mens. Writing notes. Each observation raises more questions. How does the fungus know? What does the ant experience? Will we ever understand? Researchers describe emotional impacts of studying zombie ants. You can't help but empathize with the ant, says one graduate student. You watch it struggle, fight against its own body. You know it's just an insect, but the violation of autonomy is disturbing. I've watched hundreds of infections, says another researcher. It never becomes routine. There's something fundamentally wrong about it that affects you viscerally. Some researchers report dreams about losing control, about being manipulated. The zombie ant becomes a metaphor for human fears about autonomy and identity. Indigenous peoples have long known about zombie ants. Brazilian tribes, the Kayapo people, call infected ants ghost walkers and use them as indicators of forest health. High infection rates suggest ecological imbalance. Thai communities, traditional medicine uses certain cordyceps species, though not unilateralis, for healing. Local knowledge includes which species are beneficial versus dangerous. African folklore. Some cultures have stories about cursed insects that walk to their doom, possibly inspired by zombie ant observations. This traditional knowledge often predates scientific discovery by centuries. Indigenous peoples understood the phenomenon, even if they didn't know the mechanism. Different cultures interpret zombie ants differently. Animistic interpretations: some see it as spirit possession, the fungus as a malevolent forest spirit punishing ant greed. Moral lessons: stories use zombie ants to teach about the dangers of straying from community, of individualism over collective good. Medical metaphors: traditional healers sometimes reference zombie ants when explaining mental illness or behavioral changes. These cultural interpretations remind us that science isn't the only way to understand natural phenomena. Protecting zombie ant systems requires protecting entire ecosystems. Canopy integrity: both ants and fungi need intact forest canopy. Selective logging, that seems sustainable, can disrupt the vertical structure both organisms require. Microclimate preservation: the precise temperature and humidity requirements mean even small climate changes can eliminate zombie ant systems. Trail networks: ants need established trail systems for the fungus to target. Habitat fragmentation breaks these networks. Biodiversity maintenance: the system requires not just ant and fungus, but the entire community. Trees for nesting, plants for foraging, other organisms that maintain forest health. Zombie ant systems serve as ecological indicators. Forest health: presence of normal infection rates suggests healthy ecosystem. Too high suggests stress. Too low suggests disruption. Climate impact: changes in infection patterns can indicate climate change effects before they're otherwise apparent. Pollution levels: some researchers suggest infection rates respond to air and water quality. The fungus might be more sensitive to pollutants than ants. Biodiversity status: the presence of multiple zombie ant systems indicates high biodiversity. Each system represents numerous co-evolved relationships. Conservation biologists increasingly recognize that protecting charismatic megafauna isn't enough. Preserving processes like zombie ant infections maintains ecosystem function. Future technologies inspired by zombie ants: biological robots. Rather than building robots, we might control living organisms for tasks. Insects controlled like zombie ants could explore dangerous areas, deliver medications, or perform microsurgery. Behavioral medicine: understanding precise behavioral control could revolutionize psychiatry. Instead of crude pharmaceuticals, we might develop targeted behavioral modifications. Agricultural management: controlled pest behavior could replace pesticides, make pests leave crops rather than killing them. Neural prosthetics: the fungus's ability to interface with nervous systems might inspire better brain-machine interfaces. These applications raise ethical questions. Consciousness concerns: if we control organisms, do we have obligations to their consciousness? If it exists. Slippery slopes: where does beneficial medical treatment end and unethical control begin? Environmental impact: released controlled organisms could have unforeseen ecological consequences. Human applications: should human behavioral control ever be acceptable, even therapeutically? Future research directions: consciousness studies, using zombie ants to understand the neural basis of consciousness and free will. Evolution experiments, watching new zombie systems evolve in real time as climates change. Synthetic biology, creating artificial zombie systems to understand the minimal requirements for behavioral control. Ecological modeling, using zombie ant systems to understand complex ecological interactions and predict ecosystem responses. As you prepare for sleep, consider that dreams are a kind of natural zombification. Your conscious control recedes. Your brain creates scenarios you don't choose. You perform actions in dreams you wouldn't while awake. But unlike the ant, you wake up. The possession is temporary, reversible, even beneficial. Dreams might process emotions, consolidate memories, solve problems. Your temporary loss of control serves you, not a parasite. Or does it? Some theories suggest dreams serve evolutionary purposes beyond individual benefit. Maybe we're all zombie ants to our genes, our cultures, our unconscious drives. The difference is subtlety, not kind. Understanding zombie ants might be protective. Knowledge of manipulation makes us less susceptible. Recognizing influence helps us resist it. The ant can't understand what's happening to it. It can't conceptualize fungal control. We can. That conceptualization might be our defense against our own zombification. Yet knowledge has limits. You know advertising manipulates you, but it still works. You understand cognitive biases, but still fall prey to them. Consciousness of control doesn't necessarily mean freedom from it. Carl Jung proposed a collective unconsciousness shared psychological structures across humanity. The zombie ant might tap into this deep layer. The fear of losing control, of being puppeted, appears across cultures. Possession stories, mind control fiction, zombification myths, they're universal. The zombie ant makes visceral what we've always feared. But there's also fascination. We're drawn to zombie ant stories, not just from horror but from recognition. We see ourselves, minds controlled by forces we don't fully understand, acting against our interests, serving purposes not our own. After all our exploration, the zombie ant teaches us. Behavior is chemical. Our sense of free will might be illusion. We're all following chemical commands, just usually our own. Individuality is fragile. The boundary between self and other is more porous than we imagine. Evolution is immoral. Nature produces wonders and horrors with equal indifference. Connection has costs. Being part of ecological webs means vulnerability to exploitation. Knowledge is limited. Despite decades of study, mystery persists. Life is creative. Evolution finds solutions we couldn't imagine. Questions that remain. The hard problem. What is it like to be a zombie ant? Does subjective experience persist? The evolution problem. How did such complexity evolve gradually? The specificity problem. Why such precise host-parasite relationships? The consciousness problem. Does the fungus have any form of awareness? The ethics problem. How should we treat organisms whose consciousness is uncertain? The future problem. What other behavioral manipulators remain undiscovered? Studying zombie ants changes how you see the world. Every ant becomes potential victim or survivor. Forest floors become battlegrounds. Fungi become potential puppeteers. Behavior becomes questionable. Whose idea was that really? You notice your own behavioral patterns differently. That craving meanness, is it yours or your microbiomes? That mood, is it you or your hormones? That decision, was it free will or chemical determinism? The zombie ant makes you question the nature of self, will, and consciousness. It's disturbing but valuable. Comfort comes from avoiding these questions. Wisdom might come from confronting them. The zombie ant represents existential horror, not death, but loss of self while living. It's the nightmare of being trapped in your own body, while another drives. It's violation at the most fundamental level. Yet this horror is entirely natural. Evolution produced it through the same process that created butterflies and birdsong. Beauty and horror aren't opposites, they're different faces of nature's creativity. The ant doesn't experience it as horror. It likely doesn't experience it as anything we'd recognize. The horror is our projection, our empathy extended to a creature whose experience we can't truly know. Accepting the zombie ant means accepting nature as it is, not as we wish it were. Nature isn't kind or cruel, it simply is, exploring every possible way for life to continue. The fungus isn't evil. It's just alive, doing what evolution shaped it to do. The ant isn't tragic. It's just part of a cycle billions of years old. The system isn't wrong. It's perfectly natural. This acceptance doesn't mean approval. We can recognize nature's amorality while maintaining our own moral frameworks. We can understand the zombie ant while being horrified by it. Despite the horror, there's wonder in the zombie ant. Wonder at the precision of control. Wonder at the complexity of interaction. Wonder at evolution's creativity. Wonder at life's persistence through any means. The zombie ant represents life's determination to continue, to reproduce, to persist. The fungus found a way to thrive in a competitive world. It's horrible and wonderful simultaneously. We end where we began, with an ant climbing against its will. But now you understand the mechanism, the evolution, the implications. The mystery deepens with knowledge rather than disappearing. Right now, in rainforests worldwide, the drama continues. Spores fall. Ants become infected. The controlled climb begins. Death grips are initiated. Fruiting bodies emerge. The cycle continues. It's been happening for millions of years. It will continue for millions more. Long after humans are extinct, zombie ants will still climb to programmed deaths, serving fungal purposes in the endless creativity of evolution. As sleep approaches, you surrender control temporarily. Your conscious mind recedes. Dreams will drive your mental behavior. You'll experience without choosing, but you'll wake tomorrow with autonomy restored. The ant won't be so lucky. It reminds us that consciousness and control are precious, temporary, fragile gifts. Let sleep take you gently, grateful for the morning's return of will. The zombie ant fungus exists. Right now, real ants are being controlled by real fungi. It's not fiction or metaphor but biological fact. This reality is disturbing and fascinating, horrible and wonderful. It challenges assumptions about autonomy, consciousness and identity. It reveals nature's creativity and cruelty. You now carry this knowledge. The zombie ant has infected your consciousness, not with spores but with awareness. You'll never see ants, fungi, or free will quite the same way. That's the zombie ant's gift. Disturbing knowledge that enriches understanding. Horrible truth that deepens wonder. Existential challenge that promotes gratitude for consciousness, control, and the precious illusion of free will. Sleep now and dream your own dreams. Wake tomorrow as yourself. Be grateful for that simple miracle. The ants remind us it's not guaranteed. In nature's endless creativity, zombification is just another strategy. In evolution's vast experiments, mind control is simply useful. In life's determination to continue, horror becomes normal. The zombie ants march on, forever climbing, forever controlled, forever reminding us that autonomy is exception, not rule. And yet we wake each morning, ourselves again. That might be the real miracle.